Hello, my name is Jared Longfox with Joe Kenrick here. We are the co-hosts of the AIAA Space Resources webinar series. Um, we are the co-chairs of the AIAA Space Resources Technical Committee's Education and Outreach Subcommittee. Um, and Joe has more to say about himself and the awesome work he's been doing, but based on that, I think I can just kick it on over to you whenever you're ready, Joe, and I'll lurk in the background.
Awesome. Can you see that?
I can see that.
Awesome. Thanks, Jared. And thanks everyone for joining. So as Jared said, we're both co-chairs of the AIAA Space Resources and Technical Committee on the Education and Outreach um, board. So this webinar series was put together to really start to bring technical information out to the public, try and disseminate it in a way to really increase that public awareness and education about space resources. However, today I'm wearing my normal job hat at Lunar Outpost, talking about Australia's first lunar rover. It's in the consortium called ELO-2 that is behind this rover that is called Roover. So quick agenda. I'll talk about myself just real briefly, kind of explain my background and why I'm the one talking about this today. Then I'll explain who ELO-2 is and who Lunar Outpost is. Talk about the Moon to Mars initiative, which is the sort of umbrella covering this Roover program. I'll spend some time talking about the mission and then some of the work that our consortium has done up to this point for that mission, and then kind of a look ahead, the work still to be done up to launch. And because this whole webinar series is about education and outreach, I have a couple slides on just some of the outreach that we've done under this program, because that was also a really important pillar for the program. And I'll try to make sure to leave plenty of time for questions at the end. So real briefly, my background, I actually started in oil and gas. I got a bachelor's in petroleum engineering from the Colorado School of Mines, worked in the oil and gas industry for a number of years. Really taught me a lot about resources, energy, operations, economics, and did a lot of sort of data work that kind of transferred through a lot of my career, but ultimately decided that space was vastly cooler. So went back to school at the Colorado School of Mines and got a master's in space resources. Um, Show some picture there of a weather balloon I sent up to space to capture some pictures of the Earth from about 100,000 feet. When I started doing those sort of hobby things, I just fell in love with space, so I was pretty hooked, and ultimately became a sensor manufacturer at Lunar Outpost, just anything I could do to get in the door, and eventually worked my way up to be a space resources engineer, working on a variety of NASA rover programs, such as the autonomous site preparation and break the ice challenge rovers. And then was eventually selected to go out to Australia to set up our Australian branch called Lunar Outpost Oceania, which is the co-lead of the ELO-2 consortium that I'll talk about in the next slide. So I've been program manager of that office and the technical director of that program and consortium for the past 2 years. So who is ELO-2? Stands for EPE and Lunar Outpost Oceania Consortium. So EPE is our co-lead, based in Brisbane, and Lunar Outpost Oceania based in Melbourne. So it's a consortium of 21 different organizations, 20 from Australia with 11 universities. So really bringing sort of the full gambit of talent and expertise across Australia to develop this first rover. It's the largest grant in the Australian Space Agency history. So it's a flagship mission with national significance. So we wanted to make sure we were, again, really bringing contributions from all over the country to this. And I'll kind of highlight some of these partners throughout, but excellent partners, and again, happy to talk about them even further in the questions. But who is Lunar Outpost? Is the company that I actually work for here. So we build autonomous interoperable systems that enable sustainable presence in space while improving life on Earth. That's really our vision. And we do that by partnering with space agencies around the world. So we have our offices in Colorado that's on multiple NASA programs I'll talk about. We have an office in Luxembourg working with ESA, and then obviously the Australian office working with the Australian Space Agency. So we develop a lot of dual use technologies for Earth and for space. And most notably, our lunar rovers, which I'm getting really excited for because our first one is launching in 6 days. I'm back actually about to head to Florida to watch that launch of our MAP rover. It will be going to the lunar South Pole. Primary payload on that one is Nokia. We're going to be testing some LTE um, antenna on it, sort of like a cell phone, and the lander's like the cell tower, trying to see if LTE is going to be a viable communications protocol for the moon. Shortly after that, we'll have our second mission going to an equatorial region called Reiner Gamma. It's equipped with a magnetometer from Johns Hopkins Applied Physics Laboratory, trying to investigate some magnetic anomalies present in that region. We'll then have another mission with another International Space Agency going to the South Pole. But the real exciting one that I'm talking about today is Trailblazer launching later this decade with the Roover rover. So put a pin in that one because we'll return to it. Last thing about Lunar Outpost that a lot of our company is working on is the Lunar Terrain Vehicle. So this is the next vehicle that astronauts will drive as part of the Artemis program. So you can see a prototype there with some actual astronauts testing it out and some of our key partners involved in that one. So lunar mobility is really our expertise, and we've tried to bring that to Australia and have Roover really be the application of that expertise and knowledge sharing. So talking about sort of the program as a whole before diving into some of the technical specifics. It's, as I mentioned earlier, it sits under this Moon to Mars initiative. So the Australian Space Agency's Moon to Mars initiative is a $150 million venture, really aimed at Australia participating in NASA's return to the moon and paving the way for Mars. So it's about really partnering with NASA for Australia, developing space technologies in Australia through Australian and global supply chains, and really pushing forward some outreach initiatives, bringing the public along with them, because the outreach, public engagement is really such an important endeavor, particularly when you're thinking these are really taxpayer funded opportunities. So you really need the public support behind it. So the Roover mission sits under this initiative, and it's one of the key programs, and it has its own set of objectives, which really align with that Moon to Mars strategy, as well as the civil space strategy and the overall sort of NASA Artemis program. And these are really to develop foundation services rover solutions, namely to collect and analyze lunar regolith by operating an Australian asset on the moon. That's kind of the objective one of this Roover mission, but also aims to demonstrate the ability for Australia to support these international missions, stimulate that growth in Australia so that Australia has the capability to continue to contribute in this way after this mission. This mission is just the enabler for what's to come after. That's really kind of the main goal number 2. And then, as I already touched on, main goal 3 is really inspiring the public, increasing that STEM engagement, creating new career pathways and highly skilled careers, and galvanizing that sort of national pride. So this mission has that national significance to build confidence that Australia can not just partake in humanity's return to the moon, but really be a leader in the space industry. So I've implicitly kind of talked about some of the key program pillars, but as they have been sort of explicitly described in the grant program, there's really 4 pillars for this, and I kind of touch on them throughout. There's the technical, of course, right? How well does that rover design really meet the mission objectives and constraints? You have your programmatic criteria. How capable are you of actually then delivering on that rover design and delivering on the mission? And those are the 2 that you mostly think about when you think about a rover program. But 2 other really important elements of this are the commercialization. Are you using this rover program to enable commercial viability and really advance the Australian space industry and global space industry as a whole, and doing it in an economically sustainable way? And then the impact of that, which is in that sort of supply chain development, capability development, as well as sort of the STEM engagement and outreach that I'll talk about briefly at the end. Now, pivoting back a bit towards the technical. So the Rover mission, or you may have heard of it as Trailblazer mission, is really a crucial first step towards the realization of in situ resource utilization, or ISRU operations on the moon. So if generally a technical audience, but if you're not familiar, ISRU really entails the utilization of local resources available on celestial bodies, such as the moon, to sustain human activities and facilitate long-term exploration. So this mission is really instrumental in laying the groundwork and establishing the necessary capabilities for those future endeavors, particularly within the Artemis program. So ISRU plays a pivotal role in the overarching strategy of the Moon to Mars initiative. Um, by harnessing these resources that are present in situ, such as the water ice, regolith, and other volatiles, you can minimize the need for Earth-based supplies and significantly reduce mission cost, complexity, and risk associated with these space missions. So Roover really sits kind of denoted in this NASA ISRU implementation lifecycle, and the resource analysis and mining technology readiness phase, really becoming the enabling strategy and backbone to that Moon to Mars objective. So the mission is really about resource prospecting, and I'll talk about it more in the coming slides. And in technical jargon, it's about moving resources into reserves, which is basically just gaining confidence and your understanding of what resources are there, how much, but all the other factors that come with it, like can you economically extract usable quantities? Are there the legal procedures in place? So in order to get a reserve estimate and really understand the nature of those volatiles on the moon, you need ground truth. And so that's what Rover is going to do. But one of the key problems with trying to get a ground truth measurement is when you land on the moon, you cause quite a disturbance to the surface with the lander rocket exhaust and plume. So, if you're going to measure what's there, you need to understand how you're disturbing what's there. It's a bit like the observer effect in quantum mechanics. The act of measurement sort of changes what you're measuring. So we need to start with an understanding of plume dynamics. And I'll give this is a one slide brief overview. I think we'll have a more detailed presentation in the next month or two at this webinar series on this specific topic. So make sure you attend that one to learn more. But if you imagine the rocket kind of landing on the moon, you're ejecting out quite a bit of regolith, and particularly that soft upper layer, causing erosion, changing the grain size, potentially scouring parts of the surface. And the exhaust itself has volatiles that it could be injecting into the environment. So you're really kind of changing up to hundreds of meters around the lander. And that understanding of the environmental impacts due to the plume surface interactions is really critical for us to interpret any scientific measurements that we get. And that's really what this mission's about. So more specifically, again, one of those main considerations is for lander plumes effects is sort of the radial distance upon which you feel that effect. So there's some, papers suggesting up to 15 meters of direct erosion. But again, the ejecta can go much, much further. In some cases, people are estimating even kilometers away that you can get ejecta. So with supporting instruments, which could be visual, looking at wheel tracks, plume shadows, and other sort of sensors, we can start to really understand the extent of that plume effect. And so let's call that sort of science and resource objective 1. And the second main objective is around the volatiles then. So this is a South Pole mission, which means there's likely to have some level of natural volatiles. And while this rover isn't really going into a major PSR like Shackleton Ridge, there are expected to be large amounts of micro cold traps, so really small, less than a meter, that are permanently shadowed regions near the South Pole, and they may have stable conditions for volatiles that have naturally present volatiles there. Or you can imagine if volatiles are coming off the rocket exhaust, they could get trapped in those micro PSRs, and we've sort of implanted them there. So we really need to understand the difference be, um, between the natural and the implanted volatiles and how the lander affects potentially those natural volatiles. So kind of putting it all together, our notional concept is to kind of break the surface into four quadrants based on these varied micro terrain features. So as we understand it, we want to measure volatiles again and the impact that the lander has on those volatiles. So we need to appropriately discern the difference between the two. So the division here on the left is, based on whether the region is in the sun or not, and or if the region's in the lander plume or not. So you can imagine if it's, say, behind a big rock, it might be out of the lander's plume. So if it's shaded from the sun and the lander, there's a potential for undisturbed micro cold traps that would have a relatively higher potential to measure natural volatiles. So that's what I'm kind of labeling as quadrant 2 here. If it's shaded from the lander plume, but it's in the sun, it's denoted by quadrant 3. It's undisturbed surface and has a low likelihood of containing any volatiles. If the region of the surface is in the lander plume and in the sun, it has the potential to be scoured by the plume. It's unlikely to have any natural volatiles, maybe some implanted volatiles. That's in quadrant 4. And then the final quadrant 1, shows the region that's in the shade, but in the lander plume, which has a higher relative potential to contain natural volatiles and lander implanted volatiles. So the summary of that's kind of in the table on the right. So this way of thinking about the surface with those two sort of key scientific objectives that I outlined is really the basis for a notional ConOps, if you will. So this is just sort of an infographic of that ConOps exploring the four quadrants kind of labeled in Roman numerals and the objectives 1 and 2 and how we sort of go about accomplishing those. So as an example, you could see we'd want to take measurements out radially from the lander to, again, try and measure that radial effect. You might want to take measurements in and outside of a micro cold trap, in front of and behind a rock, in the lander's sort of shadow. Take measurements at different times of day, what was in sun and now isn't, and vice versa. And just trying to sort of completely what's the word? Completely sort of gather a complete data sets on volatiles, natural and lander implanted. So with this notional mission concept, the Rover mission will really advance our exploration by improving our understanding of those plume effects, providing that unique data, help sort of anchor models that we have that are really just based on remote images at this point. It would further science by advancing our understanding of regolith cohesion and strength properties. When you apply that massive force by the lander, we can sort of see what the change is, and that's how you can kind of back into some of those geotechnical properties and understand the nature of micro cold traps better. And then furthers our understanding of resources, determining if micro cold traps are really represent a resource and can bound that volatile content. So that's really I guess, the science behind the mission and really why the mission has come about and the need for it. And now, before I kind of talk about the developments in the program thus far, I think it's important to outline the class of this mission briefly. So for those perhaps more systems engineering minded, the Roover mission is a notionally Class D mission, but it's sort of a special class. Class D means that cost and schedule are of equal, if not in some cases, more important than technical risks. So it's a way of basically denoting how can we do this cheaper and faster with some reasonable level of success. So you're sort of increasing the risk profile to enable quicker returns on your science data versus, Class A mission, typically defined as either humans are involved and or it's on the orders of billions of dollars. So like the ISS or the Perseverance rover are both Class A missions where they simply cannot fail. And thus you have to spend a lot more time and money. But since Roover has such national significance and is a high priority for the space agency, there are Class B elements of this mission. So that's where that sort of custom class puts it in. Does put a little more emphasis on mission success. So our job is really to ensure that we're delivering as low of a technical risk solution as we can, given the constraints. Um, so that class really kind of determines the philosophy for development, which is sort of summarized in this slide that we like to sort of show for our engineering approach. So it starts with a risk-aware culture, where we practice informed decision making, learn as much as we can about a potential risk, and act based on knowledge. And we're not focused on eliminating all possible technical risks, but working on ways to maximize mission success with the cost and timeline constraints. And so that may mean accepting risk for innovative solutions in certain areas, but understanding that risk as much as you can. We then iterate. I'll show you in the coming slides. We have 4 prototypes in the first year to be able to iterate, design, test certain elements. Again, really understand that risk and rather than just rely on analysis, actually test it, break it, see what works, see what doesn't, and continue to sort of move through that design. I'll show a really cool graphic in I think the next slide on that. And then data driven. By doing all these iterations, prototyping and testing, you get actual data to inform your decisions. So again, you're not just kind of relying on best guesses, models, you have tangibles to really guide that design. And that the quote there, I think, kind of really summarizes it. When in doubt, estimate an emergency guess, but be sure to go back and kind of clean up the mess to get real numbers. So putting that into practice, what our development to date has been, I'll just give you a brief overview and then we'll go into more details. So it starts at the pre-SRR phase in the NASA systems engineering lifecycle, where you kind of have a notional design, for different subsystems, start to run some analysis, look at the radiation, look at camera perception systems, trying to sort of formulate requirements going into that SRR of system level performance. You then update your design, update sort of the subsystems, run analysis, actual tests, do your thermal models, get more data, update design. This was our pre-PDR design. Start to, again, now we have 4 rovers, getting more and more test data, furthering our understanding of the risk, refining those designs and models until we got to the PDR, where you then sort of run the full gambit of reliability, structural analysis. So you can see it's a lot in one slide here, but just to kind of show that philosophy of a Class D mission in practice, and how it's sort of then lended to the 4 prototypes that we've then developed. So we have the main prototype called the consortium prototype, which is the Roover Rover. It's our flight analog, and it was sort of the last one in development that took the learnings from these other 3 that were targeted prototypes. So going from left to right, you have the mass offload model. So this was just a 1/6 mass version. So it's not perfectly replicating lunar gravity, but gives us a pretty good sense of things like traction and excavation, as well as lander egress requirements, and helping us sort of verify those. And you can see the electronics box is raised to represent a realistic center of gravity for those tests. Our first prototype, then the chassis and suspension, really just helped us formulate our early ideas around the mechanical systems and mobility systems for the rover. And then on the right was a dedicated autonomy system. So really just testing the perception as well as software systems for the rover. All of those, again, kind of then plugged back into the consortium. So here's just an overview of some of the testing that we did in the stage 1 of the program, which went up to really about August of last year. We're now in stage 2, and I'll talk about that more in a minute. But a lot of subsystem testing and de-risking. We did some ConOps and autonomy testing. Got some cool slides and cool graphics in the next couple slides highlighting these. Some wheel and excavation tests, specifically kind of looking at the wheels and the excavator for the rover, and then starting to put it together in like a remote ops demonstration and perceptions and stability tests. So here's some graphics of some of those. You can see sort of in the middle on the left, like actually, verifying what is the rock diameter that we can traverse, right? Rather than just kind of analytically trying to come up with a number, we built a mass offload version and tested it, increased rock size until we couldn't do it anymore, and tried it with different wheels. You can see in the top right the excavation rig, so trying different designs, getting understanding of the geotechnical properties. And then to the left of that, the lander egress, trying different wheel sizes, different angles, making sure that our stability is there for the rover so we don't tip when we're getting off the lander. One of my favorite tests, highlighting this, is the perception one because I'm just blown away that we actually took these photos. So we got representative albedo, sort of material, regolith, bit of sand, bit of flour, bit of concrete dust to kind of replicate again, the albedo of that regolith. Got a multi-thousand kilowatt light bulb to represent the sun, and then chucked a bunch of dust in the air and took images from our actual flight cameras at different angles, put in different obstacles just to try to understand what resolution do we need, what size obstacles can we reasonably detect, what's our sort of keep out zones when looking at the sun. And as you can see, we got some pretty awesome images that to me look like the moon. But I can verify that for you in 2 weeks when our first rover is actually on the moon. And let's see, I think last testing slide. I don't know if you can hear that. Let's see.
Yep, it's well, hold on. Audio. I cannot hear it on my side.
All right, no worries. I'll just kind of talk about it. This is uh, a remote operations demonstration that we did, which is pretty exciting. The video that you're seeing right now is of our mission control in Denver, Colorado. So in Colorado, they're driving the rover, which is in Adelaide, Australia, and there's the rover there. So driving the rover from the other side of the world, enacting a 7-second delay. And so they're just driving through the rover's perception systems there, really kind of mimicking the conditions that we'd face on the moon. So if you can imagine driving an RC car with a 7-second delay, it's quite difficult. So this was a really cool test that we did. Now, putting that all together, I won't go through all the details, but this is kind of the notional design then of the Roover rover at PDR. Again, if you're familiar with the systems engineering development process, there's still a bit more design work to do as we head towards CDR, which really finalizes that design before manufacture, and that's kind of where we are now. So you can see the 8 sort of core subsystems of the rover there. Now, just a couple slides on then what's next. As I already kind of touched on, it really starts to get into the AIT, or the assembly, integration, and test. So in the systems engineering V, as it's often caused, we're near the bottom of the V, kind of near the end of the designs part of it in the next year. And then we start to sort of go up towards the product realization. So that's when you have that design and you really kind of make it a reality, starting with the components, putting them into subsystem assemblies, and then uh, system level integration and testing. So you have the full thing assembled and integrated, and then you get into the testing, which we did a lot of functional testing that I just kind of showed you some clips of. Stage 1, stage 2 is really about the environmental testing, which anyone that's sent anything to space knows. You got to make sure that the system will operate, let alone survive in these extreme conditions of launch, transit, and then on the lunar surface. So going from sort of top left across, all right, pretty typical testing campaign. We'll have the rover, we have the main sort of volatile sensor payload that we'll have to integrate to then get the full rover, where we can then start to verify those full system level requirements, such as mass and center of gravity, volume. You then put those into the main dedicated test campaigns, which are namely the vibe and shock, to replicate the conditions of launch and landing. Then the thermal vacuum acceptance qualification tests to replicate the transit conditions, as well as the lunar surface conditions where you get massive temperature fluctuations. And then the electric electromagnetic interference um, testing to ensure that there's sort of compatibility with all your electronic and communication components within the rover. Once you kind of go through a series of campaigns there, then we'll look to integrate the rover and begin sort of the final checkouts into the launch campaign, happening closer to the end of this decade. We'll be operating this rover from Australia, and will be the first time that has happened in Australia. So it's really exciting mission. That's kind of the end of the technical, but I'd be remiss as part of the AIAA education outreach if I didn't talk about the outreach at all for this webinar. But again, it was an important aspect of this program as well. So just in stage one, which was about 13, 14 months, we had a pretty massive campaign of outreach, ran some online innovative challenges where we sort of outsourced the design of the scoop to the public in an online design challenge. We went to various schools, conferences, uh, created different showcases and went to some iconic destinations and actually got a reach of 132 million that have heard about it. Upon securing stage two, we in 24 hours actually had a reach of 240 million back in December. So we already blew our own number out of the water. And to show you some really cool pictures, just briefly, with some of the key messages. One was, getting the message out there to the world that Australia is doing some awesome things in space. Getting that Australian-made certification, so verifying that this rover was designed and built and put together and tested in Australia, proving to the world that Australia has this capability now. The other one was the I can be a part of space. So this is really kind of trying to get kids and students excited about this opportunity and show that they have and this is where like the Open Innovation Challenge came in, actually letting them participate in the challenge. And then I can see my future in space. So this is kind of taking it a step further of actually creating those career pathways. So I mentioned I moved out from the US to Australia, but the entire team was hired locally. And so these are real opportunities that exist in Australia now that didn't before. And it's really exciting to see the passion that's there for it. So going out to schools saying, you don't have to go overseas to have a job like this anymore. You can do this, and you can do this in your own backyard. Now, kind of wrapping it up. I mentioned one of the other kind of key pillars was commercialization. So we really kind of from the nascent stages brought in defense and mining and other sort of secondary and tertiary markets into the consideration, as well as understanding other future applications for the rover to ensure that there is that dual use capacity. So you may have noticed companies like BHP are actually in our consortium, and we're working with them to figure out how to get to this Roover technology into an actual Earth mine. And that really becomes sort of a self-feeding cycle where we learn from the mining parts and bring it to space, and we learn from space and bring it to mining, and it helps ensure that sort of commercial viability. So it's providing Australia and its allies with access to these essential resources in both space and Earth. Now the final slide I guess I'll leave you with, and I've already touched on it, but Australia now makes lunar rovers. There's not many countries in the world that can say that. And it's because of ELO 2 and the Australian Space Agency, and that is really exciting. So thank you all for listening. Finished a bit early, so happy to take any questions.
Yeah, hey, it's dark where I'm at now, and I don't have lights in this room. Long story. So I am going to leave my camera off. But yeah, folks, if you have any questions for Joe, please throw them in the Q&A. I forgot to say that before we got started. I
Oh yeah,
apologize.
me too.
Um, oh, sorry, kids in the background. I have one question because there's not one in yet. I saw that there was, well, I think I saw online that there was like a vote for the name of Roover. Is that right?
Yeah, that's correct. There was you could submit your name, and then there was a down select to four options, and then the Australian public voted on the four options. So Roover was the winner by Australian public vote.
Which one did you vote for?
Uh, Roover, of course.
Perfect answer.
Yes.
Yeah, no, I did too. Um,
Yeah,
so
if you're not familiar, the Q&A, it's sort of next to the chat at the bottom of your Zoom. Yeah, I forgot to mention that as well in the beginning. But sorry, Jared. What were you saying?
hold on, be right back.
Okay.
Okay, sorry about that. Yeah, I don't see anything in the Q&A, but um congratulations to you and the rest of Lunar Outpost and Hilo 2 and all of Australia on all of the successes. I'm really looking forward to seeing which missions or all these missions operate. I mean, I realize the answer to this next question is going to be all of them as well, but is there one that really caught your eye for like the science that it's doing or the operations that it's doing?
That's a good question. Yeah, because they're all pretty vastly different. Um, the second mission is quite interesting to me because it's looking at these magnetic swirls that you can see with a pretty amateur telescope that has been kind of baffling scientists for hundreds of years, and we don't know how they were formed or why they're there. So it's a pretty sort of deep question that you're answering there. But my emphasis and excitement's really around the space resources part specifically, which is what the Roover mission is really about. So I really like the science behind that one.
That was actually going to be my answer too. Good taste. Yeah, Lunar Vertex is a really, really cool mission. With a cool PI. If Dave Blewett sees this, hello. So we do have a couple in the chat now. Anonymous attendee asks, has the Clips provider been decided, and when is the flight?
Yeah, good question. For Roover mission, it has not. It has for Lunar Outpost's other three missions. We're actually what's in basically called the Eclipse manifestation process right now. So over the next couple months, we are sort of putting our requirements together. That then goes into the NASA Eclipse office. They then put that call out to the Eclipse providers. They bid on it, and then we lock down our actual provider, which then locks in obviously the ride, but also the when and the where, which is why I don't have terrible specifics on those, but soon.
All right, and then thanks. The next one in the chat from Josh Newman says, what are the challenges of the blended mission class you described? Is it hard to maintain Class D expectations when there are Class B elements?
Certainly. I mean, the challenges are relatively endless. I mean, it's essentially trying to do more for less, is what it has to come down to. You don't necessarily get more money, but um, it also adds the elements like that outreach and the commercialization part that you may not sort of normally see on a mission like this. It's a lot of those Class B elements are on sort of the national pride, the national significance, and that's again where it lends to the outreach. So it's having that sort of marketing arm of the program as well is really what that sort of causes us to create. It does put some slightly higher reliability requirements on the rover. For instance, there's a 95% reliability for the minimum viable mission as defined in sort of the system level requirements. So, no, just ensuring that, our engineering is as good as it can be is certainly a challenge when you're under the resource constraints, but it's it 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 is a challenge, and we're doing the best we can with it. And the team so far has been quite successful.
Well put. Um, the next question is anonymous from anonymous attendee. What is Australia's interest in this? To demonstrate it's part of the space community? To inspire kids into science? Are there more Australian lunar probes in the works? All rovers?
Yeah, great question. I mean, short answer, I guess sort of its interest is all of those things. But really it's about sort of building the capability for Australian industry to partake in these types of missions in the future. So obviously the mission itself is exciting. It will generate good returns for the community, the global space community, get valuable data, inspire kids, bring some level of notoriety. But it's sort of what comes after. By doing this mission, Australia now has the capability to do those future rovers. So there's some that are, in the works, that will hopefully someday sort of come about for Australia to continue to contribute. I know they work with NASA a lot. Australia is a pretty big mining country, and in order to really realize the value of space resources, we're going to have to start mining. And I think Australia is really well placed to have that be its niche in the space community, and it starts with this rover.
Awesome, awesome. Next, we've got plenty in here. Josh Newman asks, the time of flight for light from Earth to the moon is about 1.3 seconds. Why do you use a 7-second delay?
Yeah, it's a good question. It varies a little, depending on the time of year and sort of the round trip. Um, But when you consider the full communication pathway, we find that seven's a bit more realistic when you go from the rover to the lander through the ground station to the lander's mission control to our mission control. It comes out to be about a 7 sort of second delay when things are well. But then you also have to sort of consider if you're driving through, say, images, you have to downlink those images, and sometimes it could take up to 60 seconds before you get that image and before you decide your next move. It's kind of the short answer there.
Awesome. Oh, hold on. I think I might have dismissed one. I didn't mean to in the chat. Oh, we're good. Never mind. Next question is, are you designing your core system on chip computer and electronics in-house or putting third-party systems together that have space heritage to reduce risk?
Yeah, another really great question. And that's where sort of the class element of it really comes in. It's every part is a trade-off of essentially risk or heritage and cost. Um, and there's certain elements of it that we want to develop in-house, to kind of touch on that previous answer I gave, because that's how you build the capability, rather than just kind of purchasing everything internationally. In some cases, it may make sense to do that where it's cost prohibitive. But that's also the benefit of our consortium, right? It's not just this one company, there's 21 organizations. So in-house to the consortium, essentially 90% of the parts are being supplied by that consortium. There's a few kind of niche parts that we'll get elsewhere. But overall, sort of a combo of developed versus sort of partners versus just COTS.
Makes sense. Makes sense. Next, is the rover itself carrying any ASA or NASA payloads?
Yep. So the volatile sensor is a NASA provided sensor. So that's kind of one of the key partnerships in this program. And that will be kind of the key integration is NASA's volatiles sensor.
Sweet. Uh, and I do have a question, but I suppose I'll read the one in the Q&A first. If I missed it, how far do you plan to drive your lander? Did I see a UHF antenna? If yes, is that for direct to Earth comms?
Assuming we drive from the lander. Yeah, so there's not an exact distance or an exact sort of requirements. It will be a lot of sort of in and around the lander based on that sort of notional ConOps I put together. We'll definitely want to take measurements getting further and further away from the lander. We're specking at least 200 meters away. Our first two missions at Lunar Outpost are going in the orders of kilometers away. So, that's within our capability. Um, this mission will be a lot of sort of on mission decision with regards to that, just depending on the data that we get back. But in the early days, a lot of the interesting measurements will be pretty close to the lander. And as the mission goes on, we'll get further and further. As far as the actual comms system, that's sort of in discussion right now because it has to be compatible with the lander. So we kind of put together a proposal, if you will, and it becomes a bit of a negotiation. But we are pretty comfortable with any method. As I mentioned, our first mission has LTE. We've used UHF, we've used X-band, S-band, K-band options for a rover of this size. To your last point, direct to Earth is not impossible, but a, you would need quite a bit of power and quite a bit of mass, and the sort of trade-off for a mission in this class probably isn't worth it to have direct to Earth for a 20 kilogram rover or 2,000 kilogram or whatever it may be, the very large LTV one. Um, that would likely have direct to Earth.
Awesome.
Great questions.
The Q&A is currently empty. And yes, great
Okay.
questions, everybody. The Q&A is empty, so I'm jumping in. You mentioned your volatile sensor, and I probably missed it in the slides, but do you have a publicly available, like, lower detection limit, like half a weight percent water kind of deal?
That is a good question. I don't believe I can share that yet because it's, as I mentioned, not my sensor. Um, but I think they are kind of coming in development of it and nearing the end. So I think more publicly available information is to come about that sensor.
Cool. Looking forward
But
to it.
but it's pretty accurate. I know they've done some Earth testing with it.
Awesome. Fingers crossed for some high concentrations.
Yeah.
Q&A still empty. We can give folks a few more seconds on that. And everybody, I don't know if oh, there's one in the Q&A, but I'm going to finish saying what I'm saying. Um, this recording will be available on the AIAA Space Resources Technical Committee's YouTube channel. So if you missed anything and want to rewatch, that'll be uploaded there within a couple of days. And the slides will be available on AIAA Engage. You don't need to be an AIAA member for that, but you do need to make an account. It's free. Um, and links to that will be in the YouTube video description, or you can just reach out to Joe and or me about that. Um, okay, now the one in the Q&A. Do you carry any LED lighting?
Another good question. We are looking at that. Yes, the mission scope is adjusted a little bit here and there, and in the beginning, micro cold traps weren't as important, so there wasn't much of a need to have any light because we were expecting for the mission to be just during the whole day. But now that there's more interest in going into more shaded regions or micro cold traps, some level of lighting is something that we're exploring to kind of help facilitate that data collection.
Cool. I have one more question because I don't see
Good.
one in the Q&A. If you were to design or pick a landing site on the moon to go explore for any reason whatsoever, just to look at it and get pretty pictures or to test a technology, investigate a science question, where would you go, Joe?
Ooh, that's uh that's pretty good. Um, Look, to give you a real good answer, I'd have to kind of get back to you, but I'll give a shout out to Kevin Cannon, who at the time was at the School of Mines, put together what's called a scenic value index. So it's basically sort of it maps out the moon and sort of generates a score on the um the cool panoramic that you can generate from that point. So if you're kind of at a mountain and you can see the sun, the earth, and a lot of the lunar surface, right, it could generate a pretty high point. And obviously the science data is pretty awesome, but I'm really just excited for this sweet picture from the lunar surface that we can get, with in this mission, the Australian flag on it would be really cool. And so a couple of the key sites from that are like um, De Gerlache, I think is one near the South Pole. It's one of the Artemis 13 sort of potential sites that had a pretty high scenic value index for a certain type of year, as an example.
No, I've looked at that work that Kevin did, and yeah, agreed. Major kudos on that. That's a really interesting approach, and would be a really good way to get some images to spur public interest too. Real unique take on picking landing sites. I really like that.
Yeah.
And a couple more have popped into the chat.
Nice.
Um, Given the national importance of the mission, have you considered lunar night survival for this rover, or not feasible at this scale?
Yeah, another great question. Yes, and so our Lunar Outpost Europe office is basically their mission is to solve that issue because it's to be able to do any sort of sustainable operations on the moon. Obviously, you need to survive the night. It is not a mission requirement imposed upon us to survive the night. And I skipped ahead. There's another question about what the expected lifetime of the rover, so I'll answer both. I did forget to mention that. It's 1 lunar day is the standard mission, so there's no requirement to survive the night. However, to your point of the national significance, plus it being our fourth mission down the line, we are generally sort of expecting to have that capability by that time. And we'll be able to kind of slowly build capability through the first three missions. And if those are starting to go well, it's definitely not off the table to try and look at this rover surviving it. As the second part of the second question answers is, or gets at, is it's a two variable equation. The lander also has to survive the night if you don't have direct to Earth comms, which at this point we don't. Because even if the rover survives, but you aren't able to communicate through the lander, you essentially would never know. So we'd have to work with that lander provider to see what their plans are too.
Makes sense. It's all a big collaboration. Um,
Yep.
and another one asks, and hi, Carl, uh, do you think that this mission will need some more ISRU and regolith experts slash scientists to work on this? If yes, then approximately at what stage of the project?
Uh, Good question. A pretty specific one. I take it that's something that you'd be interested in. Um, we we have a lot of IRCU and regolith experts and scientists, and a lot of people interested in putting further payloads on. That's not to say that we are not interested in more. Uh, right now, as I mentioned, our focus is basically securing our ride, the Eclipse um, procurement and manifestation process. And then near the second half of this year, we start to really finalize that design. And that's where we have a better sense of sort of any extra margin and our size, weight, and power that we have to then look at how can we fill that margin with payloads that then add to the mission value. So there's a couple prospects out there, but sort of the second half of this year is probably where we'll be looking at that more closely. And of course, NASA and the space agency, Australian Space Agency, come into that equation because it's their mission too. And collectively, we'd kind of decide what is the most complementary data that we can get to the data that we're already getting.
Makes sense. Well put. And good question. And the last one we'll field here is how many people will be involved in rover operations during the mission?
Yeah, another good question. So to answer like specifically while it's on the moon, we're putting together that plan for the Rover mission, but I can talk to our first mission, which again launches in 6 days. Um, we are aiming at 24/7 operations, so you have sort of duplicate roles and teams, where you have, your sort of your flight director, your pilot, your flight engineer, command and data handling officer, ConOps officer, power and thermal, and payloads officer. So it's sort of a team of there's about 7 to 8, a bunch of standby people, IT support, obviously your whole marketing team. So I guess in total might have, say 10 people on call, and then you do shifts of either 6 to 8 hours. That pretty quickly obviously gets up to about 30 to 40 people involved in something sort of 24/7. Just to use our first mission as an example, things get more efficient and easier as we go. You can start to incorporate potentially operations from other sides of the world. And make that a little more streamlined. But hopefully that kind of answers your question for now.
Awesome. Are you going to be doing any of the ops?
For mission one, I am the con ops officer. So I get to plan our traverse and kind of determine each day where we want to go, which is probably the coolest thing I've ever said and will be the coolest thing I've ever done. So I'm really looking forward to it. Keep an eye out on Lunar Outpost socials. Over the next week, we'll put a live stream to the launch, and obviously we'll be posting pictures from the first commercial rover on the moon um, in a week's time.
Awesome, awesome. With that, I'll close Q&A. I will say, Joe, if I know you won't have any time while you're in the Central Florida area, but if you do, let me know. I'd love to meet up. And with that, folks, let's wrap it up. And again, thank you for attending this AIAA Space Resources webinar focused on education and outreach. Joe, thank you for an amazing talk. And thank you to all your colleagues, collaborators. We will be putting this on YouTube shortly, so keep an eye out on our page for that. If you guys need anything, feel free to reach out via email, socials, whatever. Joe and I are here for you, and we look forward to continuing this, and we will plan to see you next month.
Awesome. Thanks so much, everyone.
Awesome. Thank you all. Have a good evening or whatever time it is, wherever you're at, everybody. Bye.